Everybody can hear me?
Yes.
Thanks. Okay, so before the introduction, please allow me to introduce the authors. So my name is Yifan. I'm a postdoc at UT Austin, and today I will present this work on behalf of the first author, Fengshu Zhang, who is a professor in Tongji University in China. And the third author, Li Zhuang, she is a research scientist in Korea Institute of Civil Engineering and Building Technology. And the last author, Derek Ellsworth, is a professor at Penn State University, and he was my PhD advisor at Penn State. So my topic here today is implications of induced seismicity to deep geothermal energy, and this topic is in the field of geosciences and petroleum engineering. And before I came here, actually just yesterday, I checked the menu, and I found that many of you may not in this field. So today I will try my best to help you understand what we have done. And so I will not kind of give too many technical details, and just by giving you the high level key point takeaways. So without further ado, so which one is the move forward? Oh, I need to press the computer. Okay, then no problem. So today I will give this presentation by following sequences. First, background motivation. Second, friction and permeability of faults. And third, mitigation of induced seismicity through soft stimulation. And finally, the characteristic of micro earthquake in the field. Okay, this is why everybody is here. Because we as humans, we demand more energy to live prosperously, and meanwhile we need better environment. We need habitable climates to live long and healthy. In the field of geosciences and engineering, there are some solutions. First, this is what happened in the field. In the oil and gas industry, the oil and gas industry has applied a innovative technology, and they use this technology to produce natural gas at fairly cheap price and also kind of efficiently. So this technology, I believe everybody knows that, is this is called hydraulic fracturing, and this technology can create new fracture network in low permeability shale reservoir. Meanwhile, it can also stimulate the pre-existing fractures, so that the shale reservoir the permeability of shale reservoir is increased, and a result of that, the gas production is increased. So that's why in the morning kind of lecture, we found that in the United States, the shale reservoir kind of production is really high and result in very low price of that energy resources. So we know that there is unlimited geothermal resources underground in deep earth. So we're thinking that maybe we can borrow the technology from the oil and gas industry and apply that to the geothermal resources to recover geothermal energy at a fairly low price. Okay, so what can we do? And people develop, this is a kind of a concept developed maybe 30 years ago. It's called the enhanced geothermal system. This is an engineering system that for recovering geothermal energy in high temperature rock formation. So what are we going to do? We will drill a well, and that well will deep to high temperature rock, maybe 200 degrees C, 300 degrees C, and then we pump in a large amount of cold water and stimulate this reservoir. And this reservoir just rocks, low permeability rocks, and we let the fluid migrate, and basically this fluid can be water or something else, maybe CO2. We let the fluid migrate through the fracture network and get heated by rock, and then we pump out these hot fluids for generating electricity. So one issue has brought serious concern, which means that something happened in the oil and gas industry, in the oil and gas reservoir can also be happening in the geothermal reservoir. What's that? This is kind of induced earthquakes by large amount of fluid injection in subsurface. So how does this induced earthquake occur? So here's a kind of very simple figure that shows the process. When we inject a large amount of fluid in subsurface, the fluid will migrate through the fracture. And when we pump in the fluid, then the pore pressure will increase and will push the fractures apart. So that means the effective stress acting on that fracture surface will decrease. When that effective stress decreases to a certain point, to a kind of critical point of stress, then two sides of the fracture will slide along each other. And then what happened? An earthquake happened. And that earthquake happened because of this shearing. So there are two types of earthquakes. The first type is called seismic earthquake, which means that the seismic energy will be released immediately within microseconds so that you can use geophone to detect the energy. You can even feel that shaking. Or there's another type of earthquake, which is called a seismic event. What does that mean? It means when an earthquake or a fault is reactivated, it will slide slowly and release the energy, maybe the same amount of energy, but over a long term of time. As a result of that, you may not even detect that. But something has happened, right? You just doesn't know, you just don't know. Okay, so in that process, we want to know what control that process. So this is control. So the physical process of sliding or of shearing is controlled by one parameter, one property. It's called friction. And there are two frictional parameters or frictional properties. One is called frictional strength, which we can use a law. It's called Mohr Coulomb Law to describe that. And the frictional strength is basically the mu here. It's just a friction. Everybody knows friction. You just try to slide something, you feel resistance. That's friction. A second thing is frictional stability. It's indexed by the MSB value here. So there are two kind of options. When MSB is greater than 0, we call that velocity strengthening. So that means MSB is a function of frictional change with respect to velocity change. When that is greater than 0, it's strengthening, which means when you have a fracture, you try to shear that. You increase the shearing velocity, but you find it even more difficult to shear that. So that's strengthening. And it corresponds to a seismic event. Okay, second option is that if MSB is smaller than 0, what happened? It means that when you slide a fracture even faster, and you found that the friction dropped, that means it will slide even faster. There's less resistance because of that velocity change. So we call that velocity weakening. As a result of that, seismic event will occur. So that means that's something you will feel when an earthquake occurs. Seismic energy released within a second, within microseconds, immediately. Okay, we know that physically friction is a function of surface contact because you have two surfaces of a fracture. Now we know that surface contact also controls fluid flow, so that we want to know what controls fluid flow. Okay, now permeability is a kind of quantitative parameter that can describe fluid flow in a fracture. So we know that there must be interaction, or there must be a coupling between the friction and permeability. So now let's talk about friction and permeability of faults. So what controls friction? We collected a lot of rocks from all kinds of reservoirs, shale reservoir, geothermal reservoir. We powdered them, and then we analyzed the mineral composition of these rocks. And we found that we can basically classify, we can group these mineral compositions into three groups. The first group, strong phase mineral, which is called tectile silicates, for example, quartz, feldspar, some high strength minerals. And we have another kind of mineral group, it's intermediate phase minerals, carbonated minerals, dolomite, calcite. We have weak phase minerals, which is basically composed of clay. So we run some experiments. What experiment? We run the powder or simulated fault gouge by shearing this material. And we try to see what's the friction response of that shearing. And we found that this shearing, we can use some index to represent the result. Okay, we use AMSB value. This value, as I mentioned before, it tells you whether it is seismic event or aseismic event. We found that this AMSB value increases with phyllosilicate mineral content, or this increase with clay content. That means if you have a fracture or fault is rich in clays, it's really likely that the seismic event, it's very likely that earthquake is a seismic event, which means that when you trigger or induce that earthquake, the fractures will shear, will slide slowly, release energy very slowly over a long period of time. So we also try to understand how permeability and friction interact with each other. So we use saw-cut fractures and we run the slide experiments. Meanwhile, we measure the friction and the permeability simultaneously, and we found that friction and we found that permeability always declines with sleep. But if you change the velocity, you will find the permeability changes. And that depends on the mineralogy as well. And we made a summary here. So if the fracture is composed of strong mineral, if you shear that and increase that velocity, that permeability will increase a lot. But if you have a fracture with a very weak minerals or clay minerals, you shear that with a velocity increase, and that permeability will not change very much. Basically, no change. Okay, so we're living the real world. So I want to know what's the effect of roughness, because you cannot always have a saw-cut fracture in the field. We collect some rocks, we try to see, okay, we run some experiment, but if we run some experiment, we kind of destroy that rock. So I did an analog here. We use 3D printing technology, so I can control the roughness. I can print a lot of material, but that printing is expensive, so I basically made artificial sample using carbonated powder and cement powder, but we still based on this material. We just print that and use a mold, and use that mold to cast the new kind of rock-like material. We ran a lot of experiments, and we found that the friction changes with the roughness. If the cement is more rough, it's difficult to induce earthquake. But once it induces an earthquake, it's supposed to be a seismic, because that roughness has an interlocking effect. So we made another summary here. So if we have saw-cut material, the permeability always declines with sleep. If we have rough material, it will decline and then increase because of that kind of shearing, like a roller system. Okay, so in the field, however, in the field, we cannot measure the permeability. We can even not kind of identify what kind of, we cannot measure the friction. We cannot even identify what kind of friction is that. So, but the one thing we can control is that we can control some parameters that are associated with induced seismicity, and this is by operation, the in-situ operation. These parameters are fluid injection volume, stimulating the reservoir area, injection rate, injection depth, and stress state. Among these parameters, one of these is the most easy controllable, is injection rate. So we can play with injection rate. We can have a certain pattern of injection scheme. For example, we can continuous inject the fluid. We can stepwise continuous inject fluid. We can cyclically progressive inject fluid. Or we can stepwise pulsely inject fluid. Or we can cyclically pulse inject fluid. There are 5 schemes. And we found that if we use kind of cycled fracturing method, we generate even more complex fractures. And we have lower breakdown pressure. What does that mean? It means that, so this is just a summary. If we have a stepwise pulse method, injection method, we have a better performance of permeability increase, which implies that we have a better production because that relates to flow rate. Or if we have a cyclic progressive scheme, it shows lower amplitude of acoustic events. That means lower magnitude of induced seismicity. The better way is we kind of make a accommodation. We kind of combine both methods, and then we expect accommodation of better permeability increase or lower and lower magnitude of induced seismicity. So let's move to an even larger scale, which we try to understand the induced seismicity. So what can induced seismicity tell us? So I made two questions. The first question is, can we use induced seismicity to identify something, to diagnose something, diagnose the reservoir development? Or can we use that information to make a better strategic plan for production? And this is a real project. It's a project in Oregon. It's supported by U.S. Department of Energy, and implemented by Altarock. What they did is they inject fluid downstairs in the deep earth, and kind of this well is 3,000 meters, and they inject that, they observed microearthquakes, that they found that these microearthquakes occurred in the first round of simulation occurred in shallow reservoir. So what happened? Why in shallow reservoir? Why not in the deep reservoir? So I did a lot of analysis, and I say there might be a leak in the shallow reservoir, so that's why. So they sent a tool, a camera, to check the wellbore, and they found that there's casing damage in the middle of the reservoir, in the wellbore, and that's it. So we can use microearthquake to identify, to diagnose what happens. And they fixed the casing damage, and then they did a second round stimulation. So I mapped the induced seismicity data, and I say maybe we can convert this information to permeability map. So I developed some model, kind of numerical model, and I mapped the information of permeability, and I say, okay, the most permeable zone is where there is the densest zone of microearthquakes, so that we can use this permeability map to accommodate the production well, so that we can have the best flow path. Okay, so that's the usage of the induced earthquakes. So it's not always a bad thing. It's always, you can utilize that information. And this is my talk, and I hope if there's something bad, that's on me. If something good, that's the first orders. Okay, thank you for your attention.